Hello, today I will present a project presentation with focus on GPU acceleration. And here's the workflow of the presentation. We'll talk about the motivation, introduction of GPU acceleration, and hardware and software evolution, and some growing trend, TensorFlow information, and reference well. So, because GPU acceleration prompts fast growing in data analysis and machine learning, especially deep learning, as it requires high performance computing. So nowadays we can see some of deep learning framework like TensorFlow, Caffe, and big data analysis framework like Hadoop, MapReduce, Spark, and some other things. It requires like high computing performance. I would like a little bit talk about the Alex Select. It actually is specified for the email challenges for 2012. It actually is the first one to use deep learning convolution neural network with using multiple GPU for acceleration for model training. So it is actually popular in the area of deep learning research. So it is interesting to research the scene behind the growth of deep learning and study both CPUs and GPU unique features and the strengths, and to understand how CPU and GPU can cooperate with each other to achieve high-performance computing, and to understand GPU acceleration research area and future development. In case of application areas, it actually can cover like all science areas like mathematics and image and video processing and data mining, physics, chemistry, biometrics, medical science, and you name it. So what is GPU acceleration? It actually acknowledge and leverage unique architecture strengths of GPUs. So we have to have a background knowledge to CPU features. For CPU features, actually high frequency, core rate, and use large code size, and to minimize the latency of single thread. And so CPU is accepted for latency critical applications and with high performance on sequential code. For GPUs, it has a relatively low frequency core rate and have a smaller size caches. So it's good for the critical applications. And that it has actually have best performance on the parallel computation and high arithmetic intensity. For hardware evolution, we can observe that in transistor count, it actually have a exponential growth of number of transistors in each CPU and GPU. In 2014, you can observe that there's more than 10 billion transistors on one CPU and more than 8 billion transistors on one G4 Titan 10 GPU in 2015, and also have increasing counts of the cores number. Like you actually have even more like 60 cores in one GPU, one CPUs, in the powerful CPUs, and for the GPU, you eventually have more than 3,000 cores, and it's observed to have increasing size of caches and free stacking memory and increasing bandwidth of interconnection between for CPU and GPU communication. And researchers actually have also developed a CPU and GPU fusion system. In the features state that both PUs can actually share some memories. That means memory space can directly access from GPU to CPU and CPU to GPU as well. In case of software evolution, we can carry on the two scheduling. First one is dynamic scheduling. It actually means the decision about running the subtasks of the program or phases or code portion or particular processor units is actually taken in running time. Here's an example of the algorithm of dynamic scheduling. It's called work stealing scheduling. This means whenever a processor unit is in idle, it can actually steal a subtask from the task queue of the other processor. And in case of static scheduling, it means subtasks which are executed on a particular processor unit are already decided before program execution. This means subtask mapping is actually fixed. I will have two examples here. The first one is coding analysis. It actually extracts code features from the program and determines best work division ratio across different processor units and divide the workload into chunks for each PU using machine learning method. The other one is CPU and GPU hybrid. This means he first schedule CPUs do the task initialization and then hand over the data to GPU. And step 2, GPU will do the algorithm session and CPU will share a portion of workload. And the final step, all data in CPU and GPU is handed over to CPU for task completion. So what is the scheduling criteria? Here is some consideration. First one is the nature of subtasks. What I mean is like the nature of the algorithm we actually use for each task, like maybe it's doing like present correlation and model detection or all pairs shortest path. It may be more suitable to do it in the GPU, and computation of cluster coefficient, it may be good to do it in the CPU. It really depends on the relative performance of computer unit for load balancing and the high or low parallelism of the task, and the other characteristic of subtask phases, something like sequential or recurrent subtask, or if it is arithmetic and regular tasks. So it can actually have piloting the schedule is actually static scheduling, and the map reduce one actually it turned the map part in parallel and using in GPU or FPGA and doing the reduce part on CPU. For distributed computing, it actually created a master server and cluster worker to have a distributed computation power. So for each cluster worker, it usually have a CPU in each worker and maybe some other GPUs in the worker as well to do the GPU isolation on each worker and server. Here's some programming partner illustration for GPU. To use a GPU, actually, the programmer must first determine the data parallel version of its application, which means to determine the kernel size. After that, the data is then stored in the texture in GPU memory. Programmer and then have to passing the output size range of the computation, the specific vertex, that means the output size, is then passed to the GPU, and then the quadrilateral code is oriented parallel to the image plane. Its size is actually cover up the rectangular region of the output size. And then vectorizer which generates fragment for each pixel in the code and probably millions of fragments, and then the fragment processor will use the same processor program to compute the data and fetch the data from the texture and compute the process and output to the frame buffer. And final stage, the frame buffer will either output the results for the application or store in the texture for further process. And here's the benchmark to measure GPU isolation. The first one is SHOC. It actually scales effectively across a single processor unit to a large cluster. And purple is provide very level of optimization on different architecture or GPU computing. And linear, it covers different types of computation, parallel communication patterns, and synchronization techniques. And radar, It provides OpenCL application for studying interaction of processing units in HCS. Here is a called top 500. It lists the top 500 supercomputer and update twice a year. It used the metric is Lin-Park high parallel band match. It actually is based on the floating point operation per second. And for Green 500, it ranked top 500 supercomputer in terms of energy efficiency, based on the floating point operation per second per volt. So researchers actually use those of the metrics to determine their algorithm in this session. So here I will talk a little bit about the deep learning library implementation of TensorFlow to use GPU isolation. To use TensorFlow, Programa must first create a TF session in graph, so all the algorithm parts will be included in the session. And there is some category and examples of the operator, like adding, subtract, multiplication, and some array operation and major operation, and some other function that's already classified into this category. TensorFlow has actually spread to two scheduling the programmer can use, like the static scheduling. Programmer can use multiple GPU by specify the devices in the graph. For example, in the program example here, the user use device GPU number 2 and number 3 for the matrix multiplication, vector communication, and the adding operation on the CPU. And here is the other example as well. User can actually specify CPU to do the vector modification, dot product of two vector. So in TensorFlow, by default, TensorFlow can map nearly all the GPU memory to global memory to access. But users can actually attempt to allocate the fraction of the memory being used in the running allocation with these two parameters. And TensorFlow also offers dynamic scheduling as well. In some specific algorithm, we actually use dynamic scheduling. And the first step of the dynamic scheduling, it will once simulate the execution of the graph determined by the programmer. And step 2, it will pick up a device for each node in the graph using gravity method. The third step, the loop to device placement will generated by this simulation, and is also used at the placement for the real execution. For loop with multiple feasible devices, the placement algorithm uses a gravity method algorithm to examine the effect on the completion time of the loop of placing the loop on each possible devices. State in the Wikipedia that a gradient algorithm is an algorithm metric that follows the problem solving hierarchy of making the local optimal choices at each stage with the hope of finding a global optimum solution. TensorFlow also provides distributed system working implementation. The figure below shows the single machine and distributed system architecture of TensorFlow implementation, and it can offer asynchronous and synchronous model training. Here is the discussion and future trend. It is observed that there will be a fast-growing auto-have hardware, and the software parts algorithm techniques actually still lead manually partition the workload between different processor units, and the future trend may be a fully automated tool chains. And it is observed that there is attractive targets, mobile devices for isolation through the use of the heterogeneous computing HCSS, and the flows of HCSS may be popular as well because it helps to address the limitation of discrete system. This is the end of my presentation, and here's the reference I used it.